All right, folks, we're going to get started. I'm delighted to introduce Kristian Olson, who, as many of you know, is our new professor of geology here in the Division of Environmental Studies and Geology. Kristian started his career in Tennessee, where he received a bachelor's degree in geosciences from Middle Tennessee State University and his master's in earth science with a geology concentration from the University of Memphis. He then came north to complete his PhD at Binghamton University, which was called the character in or on the character and origin of Searles Lake evaporites. Maybe that'll come up today, but maybe not.
We'll see.
Kristian has a very professional CV, and it doesn't have much flavor in it, but he's an interesting dude and does interesting stuff. So maybe ask him about his weekends sometime. Okay, take it away, Kristian.
Down to? Got it. Greetings. Thank you all for coming. So, this past July, some friends and I published a paper. We're very excited about this paper. The community is very excited about the paper. I'd like you to at least understand why it's exciting. But for that to be the case, you really have to understand the context and the background. And so we'll get to our research towards the very end, and we'll talk about that paper. But for most of what we'll talk about, I want to highlight some of the major developments and some of the controversies since the late 19th century, as scientists have worked towards this unified paleoclimate history of the southwestern United States. Okay, and so we're going to start in 1879. The United States Geologic Survey is found. One of their first geologists is a fellow named G.K. Gilbert. And he and his friends went out west on horseback, and they came across this view. The water you see here is Salt Lake, Great Salt Lake. And then the mountains in the foreground is Antelope Island. Now, because of the receding of Great Salt Lake, it's more of a peninsula. Story for another time. And they noticed these horizontal flat features, okay, cutting across these mountains. And they concluded that these benches were cut into the rocks by waves in a much larger lake. And so they mapped these out on horseback, and it turned out it was a large lake indeed. Okay, so this is on this map, this is Nevada over here, and this is Wyoming over here. This lake covered the majority of the state of Utah. Okay, giant lake, ton of water, which is weird because now is a desert, right? Super hot, super dry. So how do we get this massive amount of water covering the state of Utah? Their answer was, well, the climate at some point in the past when this lake existed had to have been a lot colder and a lot wetter. And we knew about times when the climate was colder and warmer. Now we prefer the term glacial periods. And this was the ice sheet extending down into the US. Okay, big ice sheets. Here you see a little profile of the thickness of these ice sheets relative to the Boston skyline. Okay, so a lot of ice. And so it's a lot wetter, but you also have to trap all this water. Okay, and so in the Western US, we have what's called the Great Basin. And the Great Basin has no outlet to the ocean. So all the water that comes into the Great Basin by precipitation, it only leaves by evaporation. And so you end up filling up all of these valleys with what we call pluvial lakes. They're rain-fed lakes. So Gilbert described Bonneville. His buddy Russell described Lahontan. We're interested in a small chain of lakes in the southern Great Basin. Now, white guys had started describing these in the late 19th century. It wasn't until 1913, a guy named Hoyt Gale wrote the first synthesis paper of these various lakes. And he argued that these were a chain of lakes where you have one lake fills up with water and then spills into the next one. Okay, so they're all related. These are most of the lake records we're going to be talking about. So I figured we'd go through and I can show you what they look like. And so we start with Owens Lake. Owens Lake gets all of its water as runoff from the Sierra Nevadas. In this picture, standing in the Owens Basin, looking north, these are the Sierra Nevadas here. When Gale described this, there was still a lake here, okay? Since you're getting all this water off the Sierra Nevadas, there's pretty much always a lake. It's only drying because in 1913, they built the Los Angeles Aqueduct, which steals all of the water right here and takes it to LA as drinking water. As a result, the whole lake dried out. If you'd like to know more about the California water wars, there's a great 1974 documentary with Jack Nicholson called Chinatown. Okay, so throughout most of the past several 100,000 years, there's a lake in Owens. Okay, during extra wet periods, it would breach its spillover point here, and it would drain south into the next basin. It's called Searles Valley and Searles Lake. Searles Lake today is dry, bone dry. It's littered with these giant chemical plants. And so if we take a step back, there is a volcano. There's a caldera up here. And there's a lot of hydrothermal water coming out. A ton of dissolved solids, a lot of chloride, a lot of carbonate, things like boron. And all of that over hundreds of thousands of years is collecting in Searles Lake. And so when you evaporate the lake, you leave behind a massive deposit of salts. Okay, and these are economic salts. You use these specific Searles Lake salts in your house in detergents. It's used for glass making. And then we know where the high lake level was because of features like this. Okay, so here we're 200 meters above the current salt pan. Okay, and this very handsome geologist is standing on what is a reef. Okay, this is an algal reef, fossilized algae. And this was all deposited when the lake was 200 meters higher. Okay, now what's also at this elevation is this spillover into the next valley. Okay, so when the lake is this high, you're forming this reef. The water is also spilling into Panamint Valley. Okay, this is looking south, so this is a Panamint Range here, and all the water would be coming over these hills. Okay, it fills up this broad valley. Now this is as far as Gale got. He speculated that Panamint Lake may have also filled up and spilled into the next valley, which is Death Valley. Okay, and since then, there's been a lot of arguments about if this happened, when it may have happened. We'll get to that later. So Death Valley is the lowest elevation in North America. It's like 282 feet below sea level. It's extremely hot. And this is also where we consistently record the hottest surface temperatures on Earth. Okay, a number that for some reason keeps going up. Okay, and so despite it being today super hot, super dry, we have those similar reef deposits telling us that in the past we had lakes that were 300 meters deep, okay, in what's now the hottest place in the world. So those are lakes. We have one more place we want to talk about. It's over here. It's called Devil's Hole. This is Devil's Hole. As you can see, it's not easy to get to. There's fencing, there's barbed wire. Okay, they really don't want you to get into this hole. And that's because it's the home of the Devil's Hole pupfish. Okay, these are critically endangered species. On a good day, there's about 300 of them. Okay, and so those are our records. Okay, this is what we're interested in. Since this is, it's all in one small little region, okay, they should all tell the same story, especially because they're also linked, right? You have to fill up one lake to fill up the next lake. And so as the climate is fluctuating between glacial periods and interglacial periods, all the lakes are kind of going up and down. Okay, they all record the water coming in and coming out. And so we should be able to use all of these records to tell a nice story, right? They should all tell the same story. Now, before we jump into these records, I want to talk about what we know about these glacial interglacial cycles from a global perspective. Okay, so we're going to take a little detour to the oceans. Okay, now we all know the oceans are mostly composed of water. Okay, water is composed of hydrogen and oxygen, and we have different flavors of oxygen. Okay, elements are defined by their number of protons, and most elements have the same number of neutrons. So for oxygen 16, which makes up 99.76% of all oxygen on Earth, right? You have 8 protons, 8 neutrons, that gives you a mass of 16. Okay, this is most oxygen. But we have a weirder flavor of oxygen that's got more neutrons in it. Call this an isotope. Okay, so oxygen 18, 8 protons, 10 neutrons, atomic mass of 18. Okay, so it's a little heavier. And oxygen 16 is a little lighter. Okay, this means that oxygen 16 is going to be just a little bit easier to evaporate. Okay, if you got 2 rocks, one of the rocks is just a little bit lighter, it's going to be a little bit easier to pick it up. And if you have to pick up that rock a bunch of times, you're going to choose the lighter one. Okay, it's same concept. So seawater is always kind of evaporating. It's always going to be a little easier to evaporate oxygen 16. And so you get more oxygen 16 going into water vapor and moving over the continents and raining down. And if this washes back into the ocean, great, our system's in equilibrium. But if the climate's getting colder, that water is going to get trapped on the continents in the form of ice. Okay, as a result, seawater is going to get heavier over time. You're constantly evaporating the 16, you're leaving behind the heavy water, it gets stuck in the ocean. Seawater gets heavier. So we don't have a great record of what seawater chemistry is through time, but luckily we have a fossil record. Okay? And the oceans are chock full of these little critters, and they're all making their little shells out of the material available to them, which is seawater. And so these shells are made out of calcium carbonate, which, as you can see, it has some oxygen in it. Okay, so over time, as the seawater chemistry changes, the chemical composition of the shells are also going to change. Okay, now luckily for us, these things are just constantly dying, and they're raining down on the seafloor in order. Okay, so scientists go out and we drill cores into the sediment. It's a long tube of rock. Okay, it has all the sediment being deposited in order. And they go and they pick out these shells, they throw it through a mass spec, and they count how much heavy oxygen you have in it versus lighter oxygen. Okay, and that's what this plot is. This is the amount of heavy oxygen versus time. Okay, so today we're currently in a dry interglacial period, and so we don't have a lot of oxygen 18. But as we go back in time, the climate was colder, there was more ice, so the oceans are getting heavier. And this is our last glacial period. We keep going further back in time, we go back to another interglacial. The last interglacial is very important for us because this is the last time that temperatures on Earth were as hot as they were today, and maybe a little hotter. Okay, so we're really interested in the last interglacial. And we're really interested in the transition from the penultimate glacial period, the second to the last. And this transition we call termination 2. It's the termination of the penultimate glacial period. Okay? We're going to keep coming back to this. Okay? Termination 2 is very important. We have an age for it of 130,000 years. Okay? And so I could keep going on. We have names for all of these. Okay, but what we see here overall with these curves is there's kind of a pattern, right? There's a periodicity to these glacial interglacial climates. And so the question is why? What's driving this periodicity? So in 1976, some guys wrote a paper titled Variations in Earth's Orbit, Pacemaker of the Ice Ages. Okay? And they argue that the periodic nature of glacial interglacial climates is driven by Milankovitch cycles. Okay? Milankovitch cycles describe these small perturbations in Earth's orbit, eccentricity, the tilt of the Earth, its obliquity, and how the Earth wobbles on its axis that we call precession. Okay? These are all small changes, and they change the amount of solar radiation that's hitting the Earth, how it's hitting the Earth, which is important because the sun is the external energy source for the climate. Okay? Solar radiation is hitting the Earth. How that energy gets distributed through the system is what we call climate. And so they take changes in precession and they add it to obliquity and they add it to eccentricity. And you get this curve, right, that represents how much solar insolation is hitting the Earth. And their argument is that the periodicity in insolation matches the periodicity in glacial interglacial climates. Right? So this is a very elegant explanation for what drives glacials and interglacials. It makes a lot of people very happy. It's not perfect. Okay? There's some issues with it. But that's the nature of any good paradigm shift, right? It opens up new questions. Now, this is still, it's still a global picture, right? It's really good at explaining the marine record, right? But we don't live in the ocean, right? We live on land. And what we know from living on land is that the climates in different regions are different, right? Climate differs regionally. And we predict that future climate change is going to drive different rates of change and different types of change for different regions. Okay, so we're really interested in getting a better understanding of what regional continental climates are like during these glacial interglacial changes. Okay, so we're going to go back to the Mojave Desert, back to the Southern Great Basin, and start looking at continental records. First one we'll look at, it's called Devil's Hole. Well, we saw Devil's Hole. So in the 80s, a team sent a scuba diver down in Devil's Hole, trying not to disturb the pupfish. And they collected this piece of cave calcite. Okay, this is the same mineral that the little marine animals are making their shells out of. And what they're going to do is they're going to carefully drill small amounts of powder, and they're going to date them, and they're going to measure the oxygen isotopes, get a similar oxygen isotope curve to the oceans. Okay, this is their whole record here. Okay, kind of looks similar, right? Sawtooth pattern and periodicity. But when we look closer at termination 2, right, when we're going from a really wet climate very rapidly to a very dry climate, we see that the marine termination 2 is right here at 130,000 years. Devil's Hole, though, is at 140,000. Okay, this is a big problem. Okay, this is a major deal because, you know, if this happened like a little bit later, you could say like, oh, there's like a lag in the system. Okay, but since it's happening beforehand, the change from glacial to interglacial climate is happening before you have the right conditions of insulation to be driving the system. Okay. So they publish this in Science, and they say, the timing of specific climatic events indicates that orbitally controlled variations in solar insolation were not a major factor in triggering deglaciations. Interglacial climates lasted about 20,000 years. Collectively, these observations are inconsistent with the Milankovitch hypothesis for the origin of Pleistocene glacial cycles. Okay, this is huge. Huge controversy. Everyone was really happy with Milankovitch, but now we have a really just amazingly well-dated record here that disagrees. Okay, so what happens? Earth keeps spinning, Everyone keeps working on their respective fields, following their own hunches, but Devil's Hole will cast a very large shadow over the rest of the Great Basin research. And the other thing is that caves are really good climate records because we can date them very precisely. Okay? But they don't tell us too much about what the climate was like. Okay? You can do a bit with oxygen isotopes. We'll get water table records from Devil's Hole, but they're kind of limited in characterizing the climate. Okay, the opposite of that is going to be a lake. Lakes are awesome for characterizing the climate because just everything is falling into lakes and getting buried, and you can analyze it from a million different perspectives. Okay, but they're really hard to date. So in 1992, the U.S. Geologic Survey drills a 300-meter core at Owens Lake. They pull out just a ton of data. It doesn't matter what this is. It's one of like dozens of panels. They just analyze so much stuff. It gives you such a deep picture of what the lake and the surrounding climate was. But there's almost nothing to date. Okay, these are uranium thorium dates from ostracods, huge scatter here, huge scatter in the OSL dates. They can draw best fits through this, but it doesn't mean anything. Okay, we have no idea when this stuff's happening. And it's an important component of climate research is if there's a change in the system, you have to know when that changes so you can compare it to other parts of the system. For Owens, no idea. Sorry. There's one other proxy I want to tell you about, which is pollen. Okay, so this is a view of the Sierra Nevadas from Owens, and you see this sharp tree line here. And that's because the place is fairly hot, it's fairly dry. Okay? Trees don't want to come too far down. But during glacial periods, you widen that zone where trees can be had. Okay? And you're going to have more trees. And so you're going to have more pollen going into the air from those trees. Okay? And so palynologists go through the lake cores and they count up all your little pollen grains and they figure out what percentage to which species. And what we find in the Owens record is that there's this very sharp drop in the juniper pollen, okay? And so they're pretty sure that this has to be that termination 2, okay? We still don't know when it's happening, right? Do we link it to termination 2 in the marine record, or do we link it to termination 2 in Devil's Hole? Okay, we really don't know what to do with it. Okay. Downstream, we hit Searles Lake. In the 50s, one of those chemical companies drilled a core 900 meters all the way to bedrock. Super long core. Searles, there's a lot to date because there's so many salts. Okay, so here all the black is mud and all the white is salt. And so as the lake level is going up and down, you're getting muds and salts. In 1976, George Smith from the USGS publishes some of his best work on Searles Lake. This is lake level curve inferred from the evaporites and a bunch of other stuff. Okay. And what we see here for termination 2 at 130,000 years, instead of going from a deep lake to a shallow lake, we go from a very shallow lake to a very deep lake. Okay. This makes no sense. It also doesn't match a Devil's Hole at all. Okay, it just doesn't fit with anything. Okay. Downstream from that, Death Valley. Ken Lowenstein and his buddies drill a core in Death Valley in 1993, working in the hottest place in the world for several months to drill this core. Do immense amount of work characterizing the different environments that the sediments are deposited in, proxy for lake level, measure all sorts of other stuff, right? But this is their lake level curve. And right here at 130,000 years during termination 2, you're in the middle of a big lake. Okay? This does not match Devil's Hole. It does not match the marine record. It doesn't match Searles. We don't know what the correlation is to Owens, right? Because we don't have any idea what's going on there. Okay. So we have a bunch of records, They're all close together. They're all hydrologically linked. They should all tell the same story. They're all telling wildly different stories. Okay, huge problem. And so what do we think is going on here? This is probably related to our time series data. Okay, so here's a random plot. This is a number of people who drowned by falling into a pool versus films Nicolas Cage has appeared in. Okay, now there's a lot to discuss here. We can really argue a lot about whether or not this includes hot tubs, right? What if we adjusted for box office gross or included Nicolas Cage's very rare television appearances, okay? We could even have an argument about whether or not correlation implies causation, right? All sorts of things to discuss here. What no one would suggest is that the x-axis is wrong, right? That time is wrong. No one would suggest that maybe National Treasure actually came out in 2007, right? We all know it was the best movie of 2004, okay? There's no debate about the time being wrong, okay? We often take it for granted that our time axis is right, okay? This is not the case for geology, not the case in geosciences, because we're not recording time, right? We're calculating time, we're measuring it. It's a chemical analysis that's subject to error, and we have to make a lot of assumptions going into it. So there's a variety of different dating methods applied here. We'll talk about uranium, thorium. And so uranium is way more soluble, or it's super soluble. It dissolves into water very easily, and it will decay to thorium, which is very insoluble. It's got the same solubility as like aluminum. Okay, it doesn't dissolve in water. And so all the crystals that we're talking about are precipitating from water. And so we make the assumption that as the crystal precipitates, it incorporates uranium from the water, and then the clock starts clicking. Okay, you start building up thorium. And what we just like oxygen isotopes, we take this, we run it through mass spec, we count how much uranium-233 there is versus thorium-230, and that's how we get an age for when the clock started ticking. Okay. Now, there's assumptions based into this. One of them is we start with 0 thorium. Okay. If there is, for some reason, some thorium in the system, it's going to make the clock look like it's been ticking for much longer than it has. Okay. There's also all sorts of sedimentological issues about whether or not the mineral has lost some of this uranium. There's questions about whether or not the clock has been reset at any time. Okay, maybe the mineral dissolves and reprecipitates. All of this can mess with your ages. Okay, and so a group went to redate this Devil's Hole problem. Okay, they had some guesses about maybe what's going on with the dating here. And so they're going to redate the original piece of calcite. And then they went and collected some more cave rocks. And this time they found another hole called Devil's Hole 2, no pupfish. And they drilled these cores from above the water table. In the first study, they were about 30 meters below the water table. They had to get a scuba diver to go and get it. On the right, here's their results. In green is the original dating plus their resampling of this, and both of those match. Okay, so they replicated the original study, which is really impressive that the original study did this work so well 30 years prior. And then in blue, we have the new cave calcite that they collected. And what we see is that 10,000 year anomaly, it's gone. Okay, Devil's Hole now matches the other regional cave records, it matches insulation, it matches the marine record. The explanation here is that somehow you're getting more thorium into the water as you go deeper, okay? But whatever the case may be, this gets published in Science. They conclude The shift to interglacial values now broadly coincides with the rise in summer insolation, the marine termination, and the rise of atmospheric CO2, which is consistent with mechanisms ultimately tied to orbital forcing. Okay, orbital forcing, Milankovitch theory, it's back on the table. Okay, there's also this very enigmatic, infamous Devil's Hole record is no longer casting a shadow on the rest of the basin. Okay, and so we wanted to do the same thing with Searles. So in 2017, we drilled a new core at Searles. Searles is arguably the most chemically complex evaporite record that we know of. There's dozens of very weird, obscure salt minerals that we know very little about. And so my job on this project was figuring out how all of these things formed. I would need at least another hour just to get some of the highlights for this. But suffice to say, it included a lot of equilibrium thermodynamic modeling, a lot of sedimentology, and then we had to develop new limnologic models for how these saline lakes work. Okay, the result for all of it is we have a really good depositional model for how all of these salts form. This is a little cartoon, right, kind of illustrating it, and we're going through 5 stages here as the water's evaporating. And what you will notice from the profile is that the salts are out of order, okay? They're not being deposited in depositional order because they're changing in the subsurface. And so one of the reasons that we think the previous Searles Lake chronologies were so wrong is because they didn't know how any of this stuff was forming. Okay? They were just willy-nilly picking crystals and dating them. Okay, and so they were picking the wrong crystals. So one of the reasons that we did all this work was so we could decide which minerals are going to give us reliable gauges. And so out of 14 that I studied, 9 that we tried to date, we end up building an age model only using 4. Okay, but it's a very clean age model. On the right here, we see data from some of our collaborators on these weird organic molecules, where we get precipitation isotopes, lake temperatures, we got some pollen in here. And at 130,000 years, we see a major shift in all of these, which match the marine record, and it matches CO2 in the Antarctic ice cores. Okay, so the Searles Lake chronology is now back on track. It agrees with all the big picture stuff. Last man out, Death Valley. We can't drill a new core at Death Valley because it's a national park now. It wasn't before. That's fine because we still have the old core. It's still in great shape. And so we resampled a bunch of salts, got a couple new ages. Some of them agree with the previous model, but one of them that doesn't is very close to 130,000 years. And that shifts it from being in the middle of these big lakes to right on the boundary where you go from lake to dry mudflat. Okay. And so Searles Lake is now drying out at termination 2 like it should. Okay. This also matches insulation. It matches the Devil's Hole record. We get a very nice correlation between the water table elevation from Devil's Hole and the wet and dry conditions in Death Valley. Okay. And so all these records now match. Okay. So we published a paper in July. It's a synthesis of all the work we've done in Searles, new ages from Death Valley, a bunch of unpublished data that we collected in pollen records and strontium. Okay, and now for the first time, we have a consistent unified record for all of these lakes as well as Devil's Hole. Okay, they all show the same trend. We can now finally confidently put these hard ages to Owens Lake where we're getting changes in the pollen, okay? Because we see that same drop in juniper pollen in Owens. We see those same pollen changes in Searles. We see the same pollen changes in Death Valley, okay, which makes sense because pollen's just blowing all over the place. Okay, and then lastly, I had mentioned earlier that there's always speculation about whether or not animate in those lakes spilled into Death Valley. Some of the work we did was on strontium isotopes. They help you chemically fingerprint water sources. And so we have a very consistent record of strontium in Death Valley, but we have a couple excursions where those numbers change, and they change in the direction of Panama. Okay. And so this is the most concrete evidence yet that Panama spilled into Death Valley. That did in fact happen, and now we can say exactly when it happened. Okay. Final points. The actual paper that we wrote starts at 200,000 years ago and slowly moves forward in time and talks about what the actual climate was like in all of these places, what the evidence was for that through time, okay? Characterizing the regional climate through these interglacial cycles. Okay, everything I've talked to you about, okay, about the history, the Devil's Hole record, controversy, Searles not matching, Death Valley not matching, the dating problems at Owens, none of that's talked about in this paper, okay, because it's not science. Right? It's history of science, but it doesn't tell us, that story does not tell us about the climate in these records. Okay? That story does not tell us anything about how the physical world works. Okay? They're anecdotes. They tell us about how science works. And so, despite them not being in the paper, I wanted to share them with you because I think it's very important for students of science to get a good picture of what science actually looks like. Okay, it's messy. You will constantly be coming across multiple data sets that look like good data sets. Okay, for these records, all the science was awesome. Okay, no one dropped the ball at any point in these studies. Okay, but you will find that you have conflicting data sets, contradictory dating sets, right? And it's your job as the scientist to be able to navigate that. Okay? It requires being a good independent and critical thinker. And most importantly, it requires being a skeptic. Okay? It doesn't matter if you're reading the best journal in the world. Okay? Skeptical needs to be your default position. Okay? Because everything could be wrong. Okay? Likely some things are wrong. Okay? And so at kind of the fringes of science, super messy. Okay? You need to be prepared for that. The last point is that these lake records, especially Death Valley, Devil's Hole, Searles, these are all in the textbooks. Okay? Records going back, they're in all, at least the sedimentology textbooks. Okay? This new work is eventually going to get there. Okay? And you'll eventually come across little factoids will say like, oh, we have this chain of lakes, right? They're all telling the same story. Regional climates are all consistent. And you're going to read that stuff and you're going to say, well, duh, right? They should be, shouldn't they? Okay. But now you have a sense of what's kind of behind those little factoids. Okay. It's not these simple little pieces of information that we pull out, right? This is decades of people working, getting inconsistent findings and having to, come up with new hypotheses for what may be wrong there, new strategies to investigate it. And so it would be wise as you're reading other factoids to consider how clean those histories are. Okay, with that, I will thank you for your time and attention.